start. Yeah, that's working. It's working. Nobody on Zoom so far, but. So, hey, everybody, welcome. Computer graphics, grads and undergrads, always interesting. Experiment of have a joint course, so it's slightly above the level of only 433, slightly below the level of 533. The assignments will be slightly different. The grads will have a bit more to do in the assignments than the undergrads, but it will be the same assignment, the same, the same everything. And we were debating for a long time about TA or not TA, and I'm very, very happy. Let me introduce yourself.
Actually, my schedule is a little bit sketchy right now. It's not fixed, but I will hold 2 office hours, and high likely 2 of them will be in person and on Zoom. High likely on level 9, when Crystal assigns the rooms for TAs. Good. Nice to meet you all, and I hope you enjoy the course.
That's good, and it's the second or third time that we are teaching this course together. At least second or third, at least second, yeah. It's the 5th or 6th that I'm teaching this course, and we will talk much more about what Amira will help you discussing and what me. Some of the slides are stolen from Josh Levin, who in turn stole them from other people that teach computer graphics in the area. Vladan Koltan is an interesting character. He's academic brother of mine in the sense that we had the same advisor, and he was a very good student. I was the control group. He got his PhD when he was 18. Got a postdoc at Berkeley for a few years, then moved to Stanford, where as a faculty, where he did not get tenure because he decided that he likes more to do practical things, and he was hired as a theoretician. And then he was in charge of the research center of Intel at the Bay Area, was the director there, and yeah, you'll check his part. But he was teaching computer graphics in Stanford, and some of the slides are taken from him. And check Google for his part. He's fantastic. I mean, as if getting a PhD when you're 18 is not enough. And other people that some I know by part. Oh, course registration. Don't know if there is any issues about it. If there are, talk to me. Websites, basically we are using the Google Doc because it's very easy to update it. All the important material links I'll handle on the Google Doc. And there is Piazza that I think that everybody there, maybe people that ended in the last days are not there, but everybody should be on Piazza at this point. That's where we are putting the announcements. Now, of course, we will also have the class GitHub and the template for the assignments. There are a few examples of the assignments would be on GitHub. And theoretical homework, as if it's not confusing enough, every homework will have theoretical part. And the theoretical part will just easiest to check, and the most objective way to check is to check it when it's on Gradescope. So I don't why not using it? So sure. So Gradescope for the theoretical part, like PDFs that you'll write to solve this problem, I will use this algorithm. And here is my argument about why I'm using this algorithm and not that. That's you'll write. It's not a very tricky theoretical part. It's not a theoretical course. It will be more implementation. Implementation you'll submit on, you will use a GitHub class, and again, announcement, no class today, or a link to Zoom or whatever, you'll find on Piazza. Discussion, clarification are on Piazza, and everything else is on the Google Doc. Okay. What are we going to study in this course? We will have a few parts of the course. In some parts, we will do things like creating images that looks like this. So what are you seeing in this beautiful example, and why? These images were images that I created, and you'll create using ray shooting algorithm, which is annoyingly slow. And later on, we will do similar things, but using graphical hardware, and then everything will start to run quickly. That will keep us occupied in homework 3, 4, 5, and we'll build over a few of these tasks. What are you seeing in this image? You see that relates to material that is considered sometimes as image-based rendering. That you see a few plates over here, a few signs. Let's go to one of the other videos. Okay, you see that it's not. You see a few. You see here a few signs, a few plates on one plate. You see over here. You see over here some cartoon that you're putting on one rectangle. On another one, you see a picture of a cat. You see the chessboard on another plate. And basically, you are shooting a lot of rays and see where these rays are hitting. Sometimes they here hit one of the spheres, and you figure out how to find where a ray hits a sphere, like in this case. Or where the ray hits an image, one of the billboard, one of the plates, the signs that we're putting posters on. That will be another case. Sometimes when you'll hit a sphere, you'd like to give it some metallic object, so you'll give speckle. You will study the various types of shading, like specular shading and ambient lighting and diffuse shading, and because you see that depending on where the sun is somewhere here, there is this white spot here, and intensity that is degrading. And sometimes this ray, after it hits one of these balls, one of these spheres, we'll decide, oops, this sphere is actually made out of, is a mirror sphere. So I don't know what is the color of this pixel yet. To know what is the color of this pixel, that this pixel happens to be brownish, I don't know it yet because it just hit a sphere. I need to shoot another ray and see what are the objects that it hits. And in this case, it hits the billboard, and you need to decide the billboard that you also see over here. And you'll have to decide at which part of the billboard it hits. So that will be a slow and tedious algorithm that will use various ray shading. And once the sphere hits the mirror, or you will either decide, is this in the shade of some of the other spheres, or is this exposed to the light? and if it's exposed to the light, what is the intensity and the color, and how do I interpolate color, and so on and so forth. That would be part of the course, and that's just slow 1980s, 90s graphics, I think, of all courses. So we will cover all these parts, of course. Yes, we saw it. That would be the textbook that you can get electronically. Language of the course. Always the dilemma when I'm teaching this course, because basically if you want to get the maximum of your computer, you'll probably use C, or OpenGL and C will be the fastest, but that will, then you are changing a platform, and even though the C and OpenGL is supposed to be standard, it doesn't, and you run into bugs, and it's not nearly, and it doesn't give you the advantage in the job market that you'd like to do by saying that you know how to work with the most common language, which would be JavaScript. So we'll use JavaScript. Why? Because I'm following I'm following the big names, and that's a common language that is used in computer graphics courses. That is, at the beginning, it will be JavaScript, assuming that you have a single CPU. Or in other words, we don't care about which CPU it is. And then we'll move into WebGL, which starts to take care of the idea that you actually have a piece of hardware that knows to run graphics faster. And you don't need to have your CPU meditate on each pixel individually. There is plenty of operations that it can do in parallel and very fast. So WebGL will help us take advantage of it. And so some resources out of many about JavaScript. It's not the quickest way to test your idea. I send you an email, I hope, with some ideas that I think that are quicker to check. For your math, I recommend GeoGebra if you like it. Some people do, some don't, individual. I think that it's very cool, and I'll show a lot of demos that I made for using GeoGebra. That's to check your math and to check graphics, other part. Maybe processing is the quickest way to see examples that are running and takes care of this shading or these fragments or these splines and so on. But yeah, it's, I don't know, show me hands. How many of you worked in Java, studied Java in any courses? So you're good, it's not, okay, I don't need to talk you into getting it, right? It's, so you're okay in this part, okay, cool. So, did they say Java or did they say JavaScript? Oh, okay, okay. Take it back. How many of you have experience in JavaScript? Yeah, fewer hands, okay. Yes, so we will go very easily. We will give you a lot of templates. That's what else. And Amir has already proven his how good templates where you'll try to change the minimum that is needed and to get to the yes, sorry. Yeah, JavaScript. So, and JavaScript will have its, even with all the templates, it has its a few things to get used to, like that there are no really two-dimensional arrays. Even the one-dimensional are a bit harder to find. How do I get to pixel 17, 19? Oh, I need to play it into a formula. You're getting used to it, but if you want the quickest tools, if you know already, if you have already told them to work with MATLAB, I like it, but I wouldn't recommend that you study MATLAB just for this course. It's probably, there are many other tools that I just don't know about and can be more of more of test environment to play with. But sure, JavaScript. Grading, see several people from algorithms here. Not much to do. Late penalty, I'm always saying it usually. I'm not too much about when exactly are you submitting your homework, but they need to be graded and they need to, and sometimes there is a deadline that is, I'll really insist about and I'll tell you about it. It's more, but yes. So whether or not we include it or not, etc. Probably 6 assignments, maybe one less, maybe one more, assuming that it will be 6, depending on where the class will go. Lowest one will be dropped, similar to algorithm, except that more weight on the homework. Some students doing great at the midterm, and with the stressful time of the end of the semester, the performances go down. Some students struggle at the middle and then getting better. So there is a formula that gives more weight to the better of the midterm and the final. But that being said, even if you think that you got the grades that you have, there is still lines. I should have put it in the slide, but I didn't. It said that if you're doing terrible in the final, then your grade might go down. That is, even on top of the numerical value, if your numerical value, for example, is less than 70, it's quite unlikely. If it's less than 75, then it's quite unlikely that you'll get a B, even if numerically you are getting a B. That is, get your midterm is not planning to be extremely hard, not planning to be hard at all, no panics. Usually grades are fine, but look at the rule. You cannot do terribly at midterm. It can affect one letter grade. Okay, that's about this part. Prerequisite. If you played with linear algebra matrices, multiplying two matrices by each other, playing with vectors, dot product, cross product, everything that I'll discuss here will be, I will describe in the course, but if you know it, might be save some time when we're getting to it. Matrix multiplication. It will not save time because I'll definitely cover it, but you're less likely to get stuck with it, how they say. If you know complex numbers in the level of what are complex numbers, multiplying two complex numbers, dividing them, show me hands if you have done things like this. Most people, yeah. Again, stuff that I'll describe. How deep I will do it, it's partially depending on, it makes somehow the rotation transformation much easier. And when you do it, and when you're talking about quadrillion rotation transformation in 3 dimensions, things are really, really odd and clear. It's helpful if you are getting used to the idea that there is this complex numbers with imaginary parts, and you're multiplying 2 of them, which is like rotating one and, by the other, something like this. It can make things less mysterious. First homework will be submitted in pairs because of learning curve. It's easy if both of you will do it. So first homework will be submitted in pairs. Other later homeworks, maybe. We'll see which ones. There will be definitely homeworks that will not be, you will not be allowed to submit in pairs. But that being said, class preparation, anything out of it that I want to say? Chatting with each other about high-level ideas is always welcome. I will never think that you are cheating if you are discussing your basic algorithms with other people. And if you are sharing snippets of code that I don't care about, like how do I open a list of files on my folders? We'll give you examples if you want to take it from other places, that's fine. It's not part of the graphics course. And I'll be specific. Anything that is not part of the algorithm itself, how do I define bottoms in JavaScript? How do I, if you want to share pieces or download from the web or using all the AI programs for this part, no problems. The graphics part, and it will be clear for each homework what are the parts that I expect you to do by yourself, or at least for each pair to do by itself. That being said, brainstorming, always welcomed. Yeah, I'm not going to read it to you. That's kind of be a reasonable student, I think. That's, yeah. OK, yes. I'm not sure why this slide is here, but I don't know if there was a case that the TA was not treated with respect, but yeah. That's it. If you're getting your snippets of code from other sources, just be honest about it. It's not cheating. If it's not the graphics part, it's not cheating. But yes. OK. Again, it's not OK, depending which parts of the code. A great question that you might have asked yourself, why do I teach computer graphics, given that my research is not in computer graphics? Good question. I'm not the best person even in the department to teach computer graphics. I would think that maybe Josh would be that is doing visualization is better. Cobos Bernard, that is doing mostly computer vision, in his PhD, big part of his PhD was about colors and how do we represent and understand them. But I'm doing computational geometry for a living, which is a very big title. And yeah, and I published in algorithms that relates to computer graphics. I worked on projects that relates to computer graphics. Nevertheless, I'm not hardcore computer graphics, but I'm close enough to pass the material with, and I will not be shy to tell you about something I don't know. That's not going to take any credit that is not. There are the algorithms that I told, but taught this course multiply times. Yeah. Worked on pieces of the code that are related, worked a lot about geometric data structures that we'll use in, worked about, again, published in specific topics in computer graphics, but I will not, I don't have SIGGRAPH papers in this aspect. So, no, OK. Areas, you know, how big parts, just a bunch of slides that we'll go through to cover the, to give a hint about what is computer graphics, or what are we going to, well, you all know what's computer graphics. What do I want to put emphasize on? So think that I'll try, I will try to respect you by assuming that you are all paying a fair amount of money, and I'll try to give you tools that at least I think that are important and relevant, that to the best of my knowledge, that there is plenty of criticism that you'll be able to pass at the end of the course, but I will take, I will try not to see among it. It was a total waste of time. That is, the thing that I'll try to explain will be stuff that will be new for you. So, yeah. starting, of course, from working on 2D examples, basic transformation about it, would be to throw it to the water, about taking an image and scale it and rotate it, and basically download from GitHub, work with read file, write file of images. The first homework a bit harder. That's why I'll also suggest do take advantage of the working in pairs. So, of course, starting with images, computer graphics. Another area is, of course, how do we work with 3D objects? More interesting, triangular mesh that we'll play with. How do I represent a shape that consists of multiple triangles? We'll also talk about newer and AI representations, machine learning representations that becomes more popular recently to represent a scene around us, like NERF. I hope to get to it towards the end of the course. Of course, that would be the modeling. How do I work with a 3D objects? And there is tons of topics that I can put underneath what are the 3D objects. And of course, at the end, I want to show it as a 2D images. Maybe we'll play a bit with Oculus-like representation, which transformation. How do we want to do? How do we represent virtual reality, etc. And tons of materials that we can ask about what happened if the viewer moves or direct her gaze to another location, rotates, jump from place to place. What do we show? How do we work with enormous size of inputs? And now GPU is not the ultimate answer. We still need a lot of algorithms and a lot of data structures on top of the GPUs that you have, even if they're very powerful from themselves. And then we have the whole issues of things are moving. We want to create the feeling of movement of we pull elastic cloth from one side, and how does the cloth behave altogether? And cloth will behave differently if it's a solid part or the type of cloth that you have, and the elasticity and the different rotation. And we'll play with it, and we'll study, for example, how to imagine springs, like elastic ropes that connects pieces or vertices of the parts, and how do moving one of them influence the force on another one. And we'll see how we can animate behavior of elastic objects. Part of this thing that I didn't teach last time, and probably will talk about it, issues like registration between images, creating mosaicing, putting clouds of points together on top of each other, cloud of points that got, say, from later parts, what your Tesla is doing, putting clouds of points together to make a larger object. Issues like where do we decide if this will be one cloud of points and this will be another cloud of points that I got, for example, because this will be one slice of an MRI that chops my body at some part, and then I'm moving, and this is another slice that I got from the MRI. So I'll assume that somehow this part should, in 3D, continues to this part, and there is a surface that connects them, and maybe use another slides to know, A, what is a boundary between this cuts by itself, and B, that this part at certain height, at maybe z equals 3, connects to z equals 2, where this edge will have edges to this edge, and how do we decide about constructing for multiple layers, like medical data, what is a shape that is relevant to it, and which points connect to this point, where is a boundary out there. This is inside the shape, this is outside the shape, probably. Not too hard to guess in this example, but of course, it could be that they are connected in various ways. Maybe this will be the boundary, and this will be connected in some other parts. And, you know, a lot of how do I construct this 3D out of it. Multiple application of the 3D, of computer graphics, sometimes when a, not into a part, what do I want you to know? Lots of all the intro to computer graphics topics, like what basic transformation, everybody will understand it very easily. Rotation, translation will be very, very obvious. How do I do scaling, shearing, slightly less intuitive, rotation, quite okay in 2D. When we'll move to 3D, rotation will start to be confusing. And then we'll introduce homogeneous coordinates that have its surprising and pleasant impact at the moment that you see it. Like, I take two-dimensional data and I insist on representing it as three-dimensional data, adding these homogeneous coordinates. To the 2D points will be represented by 3 numbers. 3D points will be represented by 4 numbers. Why? Because we want to use basically hardware that likes to do matrix multiplication. And translation we cannot do by matrix multiplication unless we are using homogeneous coordinates. And once we use homogeneous coordinates, and it will become acceptable on everybody, you'll get used to, it will stop being threatening. So, of course, you'll understand what are images, the parts that some people like and some are not. We'll think about you're getting an image as a set of pixels, and sometimes it would be easier to think about each pixel as a point that we sampled some scene in this point. And sometimes we'll think about a pixel as something with an area in a region that it covered. So we'll think about it both as sampling of images as well as representing the whole image. And it will have impact. It will have impact because we'll study that there are correct way to fight rasterization, to fight staircase and discretization, namely anti-aliasing could be done in various ways. It will bring us to talking about suddenly special frequencies, spatial frequencies. I'm not sure that my accent is clear enough. Spatial frequencies about how fast our things are changing when I'm moving on the image from left to right. Why will it be so useful? Because once I realize that that I can capture how fast or what are the frequencies that I'm checking, I also know what the limits of when will I have aliasing and anti-aliasing effects. I know how to handle it much better. And mostly I'll be able to do image enhancement and reconstruct images in wonderful ways that even though your monitor can display only 255 or so values of color in each one of the channels of the RGB, you can essentially show images that have a much, much larger dynamic range with the correct preprocessing. So that would be very cool. Yeah. Image and signal, some people like, some not. And I'll try to get feedback from you if should I go deeper into the think about the image as a signal that we are sampled from. It starts to be ECE-like, we will mention Nyquist theorems, not handle it directly. We will mention compression and fast Fourier transform. I can talk about it more or less. And that would basically be in the part about enhancing, enlarging image dynamic range. Otherwise, images are very boring and much fewer details that we can actually show. A bunch of hardcore 1970s computer graphics, that's it. Right here, there is array. How do I create an image? Basically, I can think about a lot of pixels. Throughout each one of the pixels, I shoot each one of the pixels, I shoot array. And if this ray hits a whitish, yellowish wall, then I know that this pixel should be rendered as this whitish, yellowish color. Start from this. How do I know what is the first object that my ray hits? How do I know at which angle my ray hits it? I should give different level of brightness, different level of intensity, depending if the ray from my eye hits it in this direction or in this, or normal to the surface, or gazing to the surface. That's a bit less intuitive. I think that you'll all agree that if I just take a triangle, stick it in the direction of the projector, and asking how much intensity comes from this projector, well, it depends what is the direction, what is the angle between the normal to this triangle and the direction to the source of light, the projector, the sun. Of course, as I change it, it gets less and less intense because there are fewer and fewer photons on it. How do we actually compute it? It will turn out to be just the dot product of two vectors, but you'll have to know how to compute these vectors. Okay, and that will be way basing. We'll see a few data structures that will help us do a lot of this. And this processing, like quad trees, that some of you, I'm sure, saw with me, or like quad trees or BSP trees, or binary space partitions in general, various cell partitioning. And then we'll move into how do I actually show large images. Well, I want to not only ask what is this ray that just hit the whiteboard. I don't want necessarily to think about the whiteboard as one smooth surface. Actually, I'd like to think about an image that is stuck to this whiteboard and you see in this scene, like the one that you saw before. Why? Because basically that's how graphics works. It's the only chance to render a really large scene is to pre-process the graphic scene into large enough images, namely image-based rendering. We'll have to break the graphic scenes into scenes, images that we can stack on different pieces. And from now on, we can ask, hey, all the objects that are on the other side of the whiteboard that you want to render, pre-process this image, and if the player in the computer games that you are designing is standing and walk and gazing into whatever happens on the other side of the wall, let's pretend that this wall is not opaque but transparent, at least partially transparent, and show some images that we pre-processed earlier to do it. But what happens if I do a few buildings? I drew a few houses. Here is one house, and here is another house that you partially seen over here, and this black house is closer to where you are than the blue house. Well, you drew the images once, but now I move a bit, and of course, it will look very strange if these two houses that are not the same depth for me will stay exactly the same. So I cannot, solution, I cannot draw the house as one single image. I'll put two different plates around it, one with a blue house and one with a black house, and the black house is closer to you. Two flat plates, but each of them has a texture that describes the details of the house. That doesn't sound very bad. Okay, that's texture. Texture will play a lot, many, many rules, much more than just to make the surface smooth or rugged surface, but we'll use texture a lot. Okay, so I'll draw two images, one for this house, one for that house, and these two images are one from each other. That's great, but images, usually when you render them, they will be rendered on geometric primitive like a quad, that's kind of a quad, or two triangles, and these will be two triangles on itself, and if it's a quad, then how can I prevent these pixels from occlude pixels on the other image? Everybody sees the problem? I have two triangles. My houses are not only triangle, but one of them, you have the house on this triangle, you have another house on this triangle. I put one after the other, but how can I prevent the non-house pixels here from occluding the house pixels that are over here? So you know, somebody shoot it out. So so remote control, one hand. Let's show my artistic talents. House over here that I rendered on this triangle. But you see, here are the boundaries of this triangle. Another house that stands over here, a picture of this other house that's windows, and it's standing over here. So it makes sense that now if you're the viewer and you're walking around, then one house changes with respect to the other. But I do it on a triangle, and what do I do with all the pixels that are not inside the black house? How do I prevent them from occlude? The pixels that are inside the black house should occlude the remote. That's fine. The pixels that are not inside this black house should not occlude the remote. How do you do it? That's why you have 4 channels for each pixel, RGB and alpha. Alpha will say it's completely transparent. And that's fantastic. Then we can actually use, we have a bunch of images that each represent a very complicated scene, but I prepared an image, or I just took a realistic image, placed each one on a billboard. It's called imposer or billboard. And the ones that I don't want to actually have an impact of occluding anything, they will become transparent. So a ray that hits one of them will continue going. You still don't agree about it. And that takes us into material like how do we use a green screen or blue screen. You know. Yeah. So lots of the texture mapping, physical-based modeling, animation, tons of stuff that we can play with. We already had it. Exams to written exams, not very scary. I set a material, a date for the midterms, but it's up to you. I can shift it. It should cover the material of the first half of the semester, plus another buffer of like 2 weeks to see homeworks, discussing it. But any day, shoot a date to the middle of the semester, add 2 weeks, and any date there. So, and we can play with it when we are closer to the. You'll have deadlines of other courses, and my attempt would be there. Class participation. Okay, so I record things on D2L, and D2L, and D2L Zoom is not great in compress the video quite aggressively. So I'm also streaming it to Twitch. On Twitch, along ALG algorithm on Twitch, and I found it. If you now you are much more engaged and much more active when you are in the class. I mean, you will understand better, you will get nuances, and you know, if there is a material, if there is some very boring details that I highlight each and every meeting, and I think that it's really important, even though you don't think, but it's some nuances that appears in the textbook, but I just repeat it like obsessively in each meeting, then maybe there is a higher chance that it will appear in the exam or something like this. And there are class discussions, and we'll do some active learning, and I'll ask you questions. And the fact that there is a recording should be an addition. You are expected to come to the class. Maybe I'll ask from time to time, I'll take an image or just or pass a page to see who is there. Occasionally, I'm not going to do it every week or every second meeting, but or every fourth. I'll get some feeling about who is here most of the time, who barely is here. It's affects the class participation, and the class participation is something that I refuse to tell you exactly how many points it is, but here is where class participation plays. I didn't talk about grading policy, but if you'll end with N be your numerical grade. So the policy is, of course, if final grade is larger or equal than 80, and n is larger or equal than 90, then you'll end up with an A. And if final grade, final exam grade, I need to say. So if your final exam grade is less than 100, and altogether in the course you'll get more than 90, then you'll get an A. If F is larger or equal than 70, and your overall grade is if n is larger or equal than, if your final is more than 70, your overall numerical grade, homework, midterms, etc., is more than 81, then you'll get a B, or in some cases, an A. And when will you get an A? It depends on how well did you participate in the class, what are the actual parameters. I'm not covering all the options. For grades over here, if you got 79, but you were very active in the class, then there is a better chance that it will become a B, even though it's 79, and so on. You all understand. Be active in class, participate. Be active here, active in Piazza. Participate in the discussions. Anything that might help me saying, X is an A student. That it's undeniably an A student, that's an undeniably B student. So the gray area is where the class participation is something that I feel comfortable taking into account. That is, if you're close to B or close to A, or etc. That's where discussion are there. Okay, what else? We covered for it. Just to mention a few topics. How do I represent colors? RGB, CMYK, printers like small. Do I subtract colors or do I add colors altogether? We'll talk about all the geometric transformation, rotation, shear, that is skew, translation, of course, aliasing and anti-aliasing. Start from a very, very simple examples. Here is a line that I'm trying to render, but there are pixels, and the line, it's a black line on a white background. But if I'll decide that every pixel is either black or white completely, then the staircaseness-wise, the discretization would be very obvious. Of course, a better solution is to get a higher resolution screen, but given that it's a screen, then I can mitigate some of the discretization by saying, even though the line itself was completely black on a white background, actually pixels can get values that are neither fully black nor fully white. Gray area is welcomed in life, and here as well. How would I decide about the color of a pixel? Well, I can use a straightforward algorithms, which would say here is a line, pretty white line, fully black. The background is completely white. And now we mentioned pixels have there is dualities about the existence of pixels. They are both covering a region or sampled from an area both at the same time, and we'll use both of them. If a pixel is actually something with an area, then what would be the color or the gray level of this pixel? I'll ask what is the area of this pixel. Let's say that this is 1 centimeter. Think about it as 1 centimeter. Should have used inches, but I never remember what is inch and what is foot. So centimeters are easier. And ask from this area of the pixels how much of it is white. Let's say this would be 80% white and 20% lies inside the black line. Now I know what is a gray level of this pixel. I'll give the overall value would be exactly 0.8 color of the line, 0.2 line color. And that's a quick and straightforward way to do the anti-aliasing. Does this look better than this? I don't know. It looks fuzzy and blurry, so maybe it's a bit more annoying, but that's for a static image. The feeling of it's subjective which shape do we prefer. For a static line, I don't know if I prefer this one that uses gray values versus just a staircase one, but if my line just moves a bit, and I'll use a discretized version that every pixel is, what would be, say, the alternative? I'll look at the pixel as a point, and if this point, the center of the pixel is white, then the pixel will be fully white. If the center of the pixel is in the black, it will be fully black, which is maybe how I'll generate this line. except that now if my line moves a bit, or the viewpoint moved a bit, suddenly you'll see a lot of flickering of pixels that are jumping from black to white, which is very annoying to the eye, and that's why this gray levelish will change continuously when the line moves continuously. Shading, of course, lots of shading. 3 different parts of shading. The Stanford bunny. This is the Stanford bunny with ambient lighting. What is ambient lighting? It says that light appears and hits. You see the Stanford bunny, the same 3D models in this here and here and here, but in this part, we don't care where the light is coming from, and we don't care where the viewer is with respect to the light. We just think about the light. Maybe it's white light. It hits a blue object. As when it hits a blue object, it will mean that the viewer sees the intensity of the blue light times the intensity of the blue of the object, which is a lot, and 0 times red, 0 times blue, which will make it completely blue, and that's and what you see is just a silhouette. No idea about what is the 3D what is the 3D shape of the object besides that's the silhouette of the Stanford bunny. Next comes the diffuse shading. Let's just use this little formula that we discussed earlier that says, hey, if I'm changing my direction between the normals of the shape and where the light is coming from, then the amount of light is actually cosinus dot product of these 2 vectors, the one that is normal to this and the one that is normal to this. We'll go through it many times. Don't need to write down. Exactly, and that's enough to give you the feeling of a curvy part that is more in the shade, much more extreme when you see the sphere and 1 point source of light somewhere here. Okay, and you get much better ideas about the 3D object of the Stanford itself. But it's boring, it's done. Next, we are getting to specular light, shininess, like you painted it with lac or with shiny color, which implies that in some directions, depending on where the viewer is and depending on where the light is, we think about the surface as a mirror. Not every part of the model has this mirror-like behavior, but if you are here is a part of the bunny. That is, the bunny goes over this. Here is the light. And here is a viewer. So a ray of light that hits the bunny and is reflected and is directly reflected to the viewer, essentially that's this angle and these angles are alpha and beta. If alpha equals beta, then I'll think about this piece of the bunny as a perfect mirror. Just this tiny piece of the bunny. And it depends on where the light is, where is a bunny, then I'll think about it as a perfect mirror. If the light is white, then this part, independent of the original color, this piece of the bunny will be white as well. And this is true when alpha equals beta. It's true if I want to create this effect, even if alpha is very close but not identical to beta, then I'll still see the shininess. That's why you see the shininess behaving even on smooth curvatures, but I need now to play with guesstimating what is a normal to each part of the bunny over here. So that would be these white things are the specular spots. Why do you have a specular spots over here? Because the direction of the light is the direction to use the viewers. That's how you add the specular spot. And A, the picture looks much more exciting. And B, you have much better ideas about the 3D structure of the bunny over here with the specular shading. And we'll play with the math about it. And oh, that was a bit quick. I wanted to show you one quick example, but if this computer will collaborate. Okay, it will wait till next time. Or yeah. So your first task will be to take an image and to first to read it, and it will appear. The image will be in a format called ppm, which the idea is that it's just ASCII character. One character would be for red, one character would be for green, one character for blue, and one for the alpha. It would be 4 characters. That would be 1 pixel, and another one, and another one. It's as close to raw data as you can. So ppm. So it's easy to read it, and we'll give you examples of how to read it. And then I'll ask you to take this image. That would be, for example, let's play with this right now. Let's say that this will be the image. That would be the source. Basically, it would be a 100 by 100 image of white background and a blue sphere about it. And I'll ask you to do something like rotating it. But before rotating it, let's just increase it into an image of size 200 times 200. Because the bugs that I see when I'm asking about this part will go on further. I want that the output will be an image of 200 by 200, but of the very same direction. And let's say that this would be the image, we'll call it A. So A, I, J would be the I, J pixel. I is the row. I will be the row. Standard confusion will be, is the lowermost pixel is the I equal 1, or the highermost row is I equal 1. It doesn't matter. I mean, you'll get used to it to start sampling. At the moment, because I want to show you the highlight, let's decide that this pixel is 1, 1, and this pixel is 1, 200. And of course, this one will be 200, 200. So you can still see it. And the same goes here. And that will be my input, and that would be my output B. And here is my code. For I goes from 1 to from 1 to 100, and for goes from 1 to 100. B of 2I to J equals A of ij. What am I doing here? I take every pixel from the source, and I copy it, take pixel 100, and I copy it into 200. Okay, so I scanned all the pixels in the source, and I copied it into pixels of the target, and all of you feel that there are various shady things out there. First, I can easily fix it by starting 0 instead of 1 if that disturbs you, but that's a small issue. Other people will complain about that in JavaScript. I cannot use this convenient way to refer to a pixel. I'll have to either use functions or to calculate where in the memory this pixel is, because you essentially have one-dimensional arrays unless you are masking it in some way. Let's ignore this part right now. I want to refer to other bugs because I always see people falling into this bug. What will this image look like? What will B looks like? I'm not going to use this part. Wow, that's old. I didn't initialize B right now, so let's assume that when I initialized, then when I initialized B will be B of ij equals 0 for every I and j. That will be the color, and I just referred to one channel here. Maybe it's black and white, so I just need the gray value. What would be the most annoying artifact here? Out of many, yes? Yeah. That the output would be, where do I actually assign value to? I take every pixel of the source and copy it to a single pixel of the target. Namely that in the area where I expect the blue ball to appear, I will have certain points that were assigned. Every second pixel has been assigned as a blue ball out there, but there is plenty and plenty of other pixels. Notice here that I'm just referring to the even index pixels, and I should have assigned values to all the other pixels. So let's suggest a way to at least avoid this problem. There is a few other ones like anti-aliasing, but at least, but ignoring anti-aliasing. In homework 1, you don't need to worry about aliasing. Tell me how to do this transformation in a. Everybody understand what's the problem? This code over there, and you all understand it now. It's surprising when I'm asking people to do this homework that are for harder transformation, it's easy to forget it. So what do we want to do to fix this issue? Yeah. So essentially, if I can treat the image, and we'll see it in a more holistic way, that there is some infinitely dense image, and I just sampled some pixels from it. We'll go into why we're going through this somehow strange approach a bit later about sampling. At the moment, we're just trying to fix not to leave pixels unassigned. So I can take the ij pixel, and copy it 4 times. That is to insert inside the two 4s another two 4s over here of 4k1 and k2 goes from 0 to 1, 0 to 1. Or the simpler way to think about it would be for I goes from 1 to 200. And what do? B of ij equals A of I half j. Everybody agree? I pick a pixel from here for the ij, and I ask, hey, what's the source of the pixel coming from here? And then I don't need these 4 loops. And that's a method that we'll use a lot of times when we are converging transformation. Okay, I am not looking at the source and copy each pixel to one or a region at the target. Instead, I'm looking at a pixel of the target and then performing what is this? The I half, j half. I'm doing the inverse transformation. Instead of scaling up, scaling down. The I half, j half ask this ij pixel, where does this coming from? It's coming from some point in this image, and I'll go and fetch the color, the gray level at this pixel, and that's what I'll copy to the ij place. Okay, that works great so far. Now, can I do the same thing if I want? So that will help me scale up, scale down, translate, especially if I want to move all the pixels by some amount to the right, and this amount is not necessarily an integer. I can still do it. At the beginning of the next class, let's talk about how do I do the same thing with rotation. What happens if I want rotating? If I want to rotate this image, I need to tell you what the axis. So after the rotation, I want this pixel, this blue ball to be rotated to someplace over here. Then the transformation that I'll use right here will not be I half, j half, but will be some simple formula that takes the I half, j half, and says, oh, this pixel over here, before the rotation, where will it come from here? And do the same trick, but with different transformation. And that will essentially cover most of the theory that you'll need for homework 1. OK. Thanks, everybody. Didn't ask any questions? Bureaucratic things, anything else?